Are we good to go? Okay, cool. Thanks. Thanks everybody for your time. We just had a discussion with some of the guys here and saying that the after lunch session is normally the graveyard shift. You know, tummies are full, eyes are heavy, and there's about 3 hours between you and some beers. So I'm going to try and make this quick. There's quite a few things we got to go through, but I think we'll keep it concise and to the point. And please, I like interactive engagement. So if you've got a question, please raise your hand, ask the question. We can address that and then move on. I think I do have a question and answers at the end, but a lot of people forget the question. You know, once we're on the topic and we discuss it, it normally comes out a little bit better. Cool. So just a quick one. So I marked it as the question. We're going to get into that one first. And this is the question I get asked most from people here at our stand. And they are saying to me, what is H3C all about? And I think will take just a minute or two to explain to you the history of the company, how we came about, and the future of what the company represents. So back in the day, and see there's a few people here that's got very little hair on myself. You'll probably remember a company called 3Com. Remember 3Com? Here we go. So we essentially are 3Com. When 3Com, the American company, were looking for a way into the Chinese market, they had to do a joint venture with a Chinese company in order to get in there. You can't just, open up an office there. So we did a joint venture with Huawei, and hence the logo. The H is for Huawei and the 3C is for 3Com. Now that joint venture only lasted a few years, and then Huawei pulled out of it, and the brand H3C still, was there, but 3Com was operated. And not very long after that, HP acquired 3Com. So to this day, we still have switches that runs our Comware software on it. And that switches are being OEM'd by HPE Networking. So we then pulled out of the South African market because HP at that point owned 3Com. The brand almost got diluted to the point where HPN was just that, HP Networking. And the brand wasn't available in the world anymore. So technically we are back in the country for 3 years now. So we are technically a startup business, if you want to put it like that. But the product and the development of the product has never slowed down. We're running on Comware version 9 already. So through the years where we didn't have a presence in South Africa, the product was evolving, more product was added, and we got to a very solid offering of a wide range of product. Something to note is that we do not acquire businesses. We are not, HP that buys a bunch of businesses, bring the technology in. What we do is we have our own R&D teams that develop product. So what you see is being developed from the ground up for our products. With that being said, everything is open standards. We don't, make things proprietary. Therefore, it's easy to integrate with our product. Cool. So if you ask the question, this is ChatGPT, by the way. I used it. I was wondering what would be a small and a quick, concise way of asking what HPC is. And it came out with this, and it was bang on with regards to my discussion. If we read it, I'm not going to read the whole thing, but I'm going to highlight the powerful processors, networks, and storage systems. Now, historically, we've seen that these things tend to be addressed in silos. We've seen that the guys from Intel and AMD has done magic with regards to, making the processors more powerful. We've got GPUs. NVIDIA's been doing awesome stuff. AMD's been doing awesome stuff with regards to GPUs. But that's where it ended, right? So we were asking earlier, this PC you see standing here, it looks like a pretty powerful gaming PC. So at what point does a normal PC or normal compute become high performance compute? There's a few rules that you need to follow for that. You need to have the processor, the network, and the storage portion needs to all come together and make HPC possible. You can have siloed approaches with very, very good hardware with regards to the graphics and the CPUs, but if the connection to the next one in terms of the network is not up to scratch, it technically is not high performance compute. It is just a small portion of it. Okay, so we have a few challenges when it comes to high performance compute. So there's a lot, okay, but for the purpose of this, we're only going to address 3 of them. We've got cost. HPC's never been cheap, okay, because we tend to live on the cutting edge of those technologies. Scalability, data management. We create massive amounts of data while we run these computations and we make these fancy math work. Power consumption is a problem. Cooling is a problem. The complexity, because there's not a single vendor that's going to give you an HPC solution that is, complete. We need to mix and match different technologies from different companies in order to give you the HPC, feel, if you want to call it that way. So the first one we're going to address is power consumption. Okay, now that leads me into a product portfolio slide. Don't read too much into this now because we are going to get into them a little bit later in more detail, just to explain to you what we do from a product portfolio. What I do want you to see and want you to look at is the fact that there's not a lot. So H3C has decided, instead of having 1,000 different SKUs and servers available, is to actually pick the ones that fits the purpose best. Okay, so if you look at the range there, you'll see the guys that knows HP will know wherever you put a 50, it's an AMD machine, right? Okay, so we've taken the same kind of an approach. So the point that I'm making is that these modular systems all uses the same power supplies. Okay, so we as H3C has about 15,000 patents. Okay, and those are innovation and invention patents. Now there's a whole bunch of those patents that applies to our power supplies. The exact number is not known, that's confidential, but the PM tells me it's a lot. So we'll take his word for that. Okay. So we also have 80 plus certifications, which means that our power supplies always at least runs at 80% efficiency. Okay. We have platinum and titanium models that goes into the back of these servers as well. Ooh, what happened there? Must be that guy. Stay away from my screen, man, please. Yes, and then we use a whole bunch of other technologies in our power supplies. For instance, like pushing up the efficiency that we can get on our titanium and our platinum power supplies. We can run at a 50% load and still achieve about a 94% efficiency rate. Okay, which makes a massive difference in terms of big clusters, big computing. That HPC is all about. We also have and a stance that we take and say, don't buy more power supply than what you need. It's easy to put a 2.6 or 2,600 watt power supply into everything, and then later on you complain about the power consumption. It's because you overspec the power supplies. So we have a wide range of power supplies, ranging from 550s all the way up to 2.7 or 2,700 watt power supplies. We also have DC power supplies, because we do recognize that in some of the telco spaces, they run off solar or alternate power sources, and we need to be able to accompany with that as well. Now, giving you an efficient product is one part, but actually manufacturing the product with efficiency in mind is a separate thing. So, I mean, it's easy to say, here's a small power supply, you not consume a lot of power, but back in our factory, we're consuming massive amounts of power and we leave a huge carbon footprint. So we have available in our manufacturing capabilities, we've got our assembly part is 90% automated. So 90% of the device that you see is never touched by human hands, okay? We have robotics and all sorts of fancy stuff that actually puts that lot together for you, and that comes with a very small carbon footprint, because the entire manufacturing process is a green process. When the automation ratio, we're looking at about, I think it's 85%, especially on our servers. Servers are also manufactured in a plant that nobody touches anything, and that leads to smaller footprint as well, and even on the packaging. Now, who's ever taken a TV out the box and then try and put it back in the box? Does it ever fit? Never goes back in the box, right? And it's because of these oaks, it's because of this, because of the fact that, it's automated, and the whole design around the packaging is around automation. Things must be in such a place where it can be automated very easily. So we partly have a hand in the fact that that damn thing just won't go back in the box. But that does bring with it a few values. It does mean that our lead times in terms of the manufacturing process is about 40% less. Okay, so we show a much improved lead time. We also show about a 35% cost reduction in the manufacturing process. And that means that we've seen on average about a 35% increase in, or decrease, let me put it that way, in out-of-box failures. Okay, I mean, I've built many PCs in my life, and if you don't press the DIMM hard enough on the one side and you switch the machine on, it's a dead machine, it doesn't go on. All those kind of things are mitigated when we use automated solutions. The point that I'm making is all of this happens in green factories. Very, very strict regulations around the carbon footprint, and that adds to the power problems that we have. Okay. Number 2, cooling. 1 watt in, 2 watts out. I think that's what they said. Eh? You put 1 watt into the power supply, you need about 2 watts to cool that scenario, right? So the problem that we have here is that the traditional way of doing air-cooled is reaching its limits. As our guys from Intel and our guys from AMD and NVIDIA and those guys put more performance into their chips, the heat signature rises. It's a fact. You can't have performance without power. Efficiencies definitely come into play as well. So how efficient are you in cooling it, and how efficient are you in using it when necessary? Also plays a very large factor. If we look at that slide there, that graph there, we can see that in 2025, we reckon that per rack, we can use up to 25 kilowatt per rack. That is an astronomical amount of power. And when it comes to high performance compute, we realized that very quickly. It isn't even a surprise. So the way that we consume energy and the way that we make use of the energy in a very proficient way, and also how we cool that, is going to become much more intensive. Okay, here's the chip consumption trends. Again, guys from NVIDIA, Intel, AMD, and all those guys do a good job at giving us high performance chips. But, you know, if you want horsepower, you need to feed them. You need to make sure the power is there. So theoretically, we're going to hit a limit whereby air cooling is just not going to cut it anymore. That hot aisle, cold aisle thing is it's just not going to make sense anymore. Because what is the object of what we do in compute? Density. We want to make everything fit into something smaller. Heat signature goes right up when we do that. Okay? So at H3C, we've got a full stack of ICT liquid cooled solutions. Now, liquid cool is not new. I'm sure that thing's liquid cooled over there. It's not something that's new to the industry. Gamers and guys that has big PCs has been doing it for many, many years. But there's always been challenges around that in the data center. If I have a leak on one PC, one machine, it's one machine affected. If I have a 43U rack full of machines and I've got a leak, many more machines gets affected. So there's a whole way of doing this in a different manner to make sure that we mitigate those risks. For instance, special couplers, special liquids, we'll get to that in a moment, leak detection sensors that's built into the environment to make sure that we can report on those leaks if something does happen, and address that problem. So the types of liquid cooling. So we've got direct cooling, which is split up into two, immersive and also spray type. Now, spray type is pretty much what you do with a radiator in your car. It's the same kind of thing. You've got a expanded metal or aluminum for those that wants to use an American surface that gets the coolant pumped through it with sprays on top of it, with air on top of that, cooling that specific medium down and then cooling in that way. Now, under immersed, there's two versions of it. We've got single phase, which pretty much means that I give you a cool liquid on the one side. That liquid goes into the rack, into the servers. It follows the process of cooling down everything on a cold plate, and then it exits the actual rack, but in a warmer condition. In other words, it still stays water. It just enters at 15 degrees and exits at 35 or 45 or whatever the case may be. When we talk about phase change, the liquid actually evaporates. And while it evaporates, it draws the heat out of the CPU or GPU or whatever that case may be. Okay, that's a changes a state, right? State goes from a liquid into a gas. That gets put through a chiller. Once it goes through the chiller, it changes back into a liquid, and that liquid then gets circulated across the solution again. Two different ways of doing that. Okay, so there's the types of coolant. There's different ways. We can use mineral oils. We can use deionized water. We can use synthetic silicone oils. Lots of different ways, but they all have some downfalls and some plus points. If we think about mineral oil, oil generally is something that will burn. Okay, it can combust, but the way that the oils that we use is put together in terms of viscosity and so on, it has a very, very high flammable or ignition point. So in other words, things really have to go bad big time before we will have a problem like that. Generally, if we look at the electrofluoride liquids, the ability for cooling is extremely strong. The electrical insulation is very, very strong. So there's a lot of stuff that you can associate with what the right way is to cool it. And yeah, it comes down to cost at the end of the day. Everything does. So from an electronic fluoride liquid perspective, the cost is high, but it comes with a little less risk. And then obviously from a mineral oil type, the cost is not that high, but there's an inherent, risk there as well. Now, I'd rather clean up the inside of a machine that has a water spill than a oil spill, if you understand what I'm saying. Okay, it's much easier to deal with that in terms of a disaster. Cool. So this is how we address that problem. Okay. So here we can see that this is a rack. This is a rack that works on two ways. We can either plumb this into an existing chiller circuit that the data center might have, or we can actually give you a chiller device per rack, which means that every single rack becomes its own data center, if I can put it in inverted commas, because that environment then is self-sufficient and it runs by itself. If there's a problem with that, only one rack is affected. If you have a plumbed-in version of the chiller and the chiller breaks down, everything connected to that is going to have a problem. Okay, so this is a high level of what we've done. There must be techies here that sat in a data center. What do you get tired of first? Being cold or that bloody noise? That noise in a data center drives me nuts, okay? So what we see here is a massive reduce in the noise level. Okay, it's below 60 decibels because there's not so much things spinning and so much things blowing and in and out and none of that stuff. Okay, now, who knows what a PUE is? It's a power usage efficiency ratio. The perfect ratio is 1, which means that the power I put in, I need the same amount of power to cool that power. That's utopia. We actually get really close to that with the solutions. We get to about 1.2. Now, from a data center perspective, some of the larger hyperscalers that use us water cooling already or liquid cooling already, they aim for about a 1.5. So we are well below that 1.5 level with a 1.2. And this was independently tested. So we're not claiming this because, we thought that sounds like a good idea. We actually had it independently tested. And data centers widely recognize that as one of the most efficient ways of cooling. Okay. So this is a case study that we did. You can read through that. I'll give you a minute. I'm not going to read everything. But the long and the short of it is, those racks, if you look up there, right up there, and down here, those are the chiller units. So those racks are self-sufficient. They can stand in 40 or 50 degree environments, and the kit inside will be perfectly safe. On average, we see an 18% drop of CPU temperature. Now, CPUs get more efficient the colder they are, right? So if you think about an 18% or 18-degree difference between that, it makes a lot more sense now. Now we've addressed two problems. We've addressed the cooling problem, but we've also addressed the power consumption problem. Because if the temperature of the CPU comes down and it runs at a solid and a stable temperature, the CPU is more efficient and needs less power. Okay. Right. Number 3, scalability. So from a scalability perspective, we are partnering with our friends at Intel and our friends at AMD. And they do a great job of making these CPUs efficient. And, one of your drivers is to make that CPU as efficient with using as little power as possible. So we partner with those guys and make sure we bring those positives into the product that we have. So when we look at our servers now, which is the Generation 6 servers, we support the 4th and 5th generation up to the Sapphire Rapids CPUs. We have launched our new Generation 7, which is what's the new? That one year. So we've got a Generation 7 server that will make use of those CPUs as well. We support DDR5 memory with 5600 clock speed, and depending on the chassis that you put this in, we have between 32 and 64 slots that you can populate, which means we can bring the density that you use typically for HPC down to a very, very small footprint. Okay, let's skip over. Right, so let's just quickly look over them. I'm not going to bore you with this. We are almost out of time. This is our workhorse. If you talk to HP and you ask them what's your workhorse server, they're going to go Dell 380. Okay, it's always going to be a Dell 380. This is the product that we have that is in that class. Multi-use machine. It's good for everything. It can take a lot of CPU, can take a lot of memory. There's lots of cards that we can, riser cards we can slap into it for GPU performances. And we also support, on the back end of this, we have 2 OCP cards, 2 OCP 3 slots, which can run up to 25 gig network throughput on the OCP slot. And then we can slot into the riser cards, we can put our 100, 200, 400, and 800 gig network interfaces. We then have an ultra version. Look the same, right? More or less. Does anybody know what this is? E1S drives. You should know. Anybody? You do? Okay, cool. So we know what an M2 drive is, right? Every laptop you have nowadays has got an M2 drive in it. This is a drive that is slightly bigger than an M2 drive, but it's an NVMe disk. And that slots onto the motherboard. Directly onto the motherboard. Okay, so no riser cards, none of that. Difference here is we can see, we've got 8 of them. In our Ultra, we've got 32 of them. That excludes the 25 drives that you could put into the front of the machine. And those can be all NVMe drives if you wish to do so. Okay, so that box is small, but it's a small lighty that can do karate properly. Okay, it is a very, very powerful machine that we can use. And that is also our flagship 2U liquid cooled server. Right. The 4700 is a 1U version of what we just saw. It's the same board, same rules, it's just in a smaller form factor. The 67 is now where we start moving into the quad processor space. Quad processor space with 64 64 DIMM slots. So I think last time I checked, we can do probably 32 terabytes worth of memory per box. Okay. So again, we're going into density. We're going into a much more dense form factor. And that being a 4U box obviously gives us loads of space for cards. And we typically can put, and I think it's on here, we can put, where is it now? I think it can take 8 full-length, double-width GPUs of your choice. Okay, so when it comes to high-performance compute, this is typically the box that we can use. Along with this is the fact that we can put, again, 25 gig networking, 100, 200, 400, 800 gig networking in this. And we support Mellanox. We support very low loss networking. We actually are a partner of Mellanox, so we've got cards with Mellanox developed chips on them. Okay, so why is it important? Right back to what we started with the first time. We said we need to bring the compute and the networking together to give us a proper HPC solution. This is how we at H3C do this. Okay. That's the G6 6900. Also, lots of memory slots for CPUs. It is just a more dense version of the previous one. Okay. Right. So what do we do for the Ethernet side, for the connectivity side? Is we have released, and it's available now, our 800 gig switches. Okay, how do we achieve 800 gig? All our switches runs on PCI 6. So the actual bus connection in the switch is done by PCI 6. Now we are hoping and waiting for our brothers and sisters at Intel to make that bus available to us on the compute side, because you can imagine NVMe drives, running at PCI 6 base, along with the memory bus. The performance is going to be incredible, but from a networking perspective, we are geared up for it already. Now, what we can do with these is obviously we can have multiple links, giving us multiple instances of those 800 gig ports. Okay, the optics for this, yeah, it's expensive, but again, performance always comes at a cost. And now we can brag a little bit, just slightly. We don't like to do that, but we can brag a bit. So we actively participate in conjunction with Forrester in a competition everywhere that's called the SPEC competition. Now, we have our own hypervisor that we use for these tests, and we have won that one since 2013. Something we're very, very proud of. Okay, from a virtualization and a throughput perspective, we've won that event for many, many years. And we're still building on top of that. Another one is the ML performance, MLPerf. It's also based on a neutral company taking some of our servers, putting them through all sorts of tests, compete them with other vendors, and we've managed, since we have started our own server standards, because remember we used to be a little bit more HP and a little less H3C, which is now the other way around. We've got 86 prizes that we've won with regards to performance. So the point I'm trying to make is that it is a very mature solution. Just because we've been back in South Africa for 3 years doesn't mean we haven't done anything, to enhance this. And just quickly, I want to give you my favorite HPC scenario or application. I'm a petrolhead, right? I like driving fast. I like watching races. I like doing things like that. So how does it work in the automotive industry? We see that when it comes to Formula One cars, one of the biggest challenges they have, and one of the most speed, where they gain most performance, is aerodynamics. Now, if you start doing aerodynamics in a wind tunnel, that can become extremely expensive because those things cost a lot of money. But if we bring HPC into the fold, we can then computate and work on those aerodynamics from a completely different standpoint. From a safety perspective, we don't typically want to crash F1 cars into a wall to see what happens to the guy inside, right? So we rather do a virtual crash to make sure that that everybody will be all right. Okay. So the real-time data analytics, we see this in action. If you're a Formula One guy and you watch Formula One racing, the strategies change every second. And that's purely because they get all the data from the car in real time. They use high-performance compute scenarios and algorithms to process that data and to predict the best outcome for the conditions that you have at that point in time. Okay. The virtual wind tunnel we had a talk about, driver simulations. Is there anybody that hasn't been in a sim of some sorts, Gran Turismo or anything like that? These things are extremely realistic, okay? Extremely. And that's because all the track data that's been gathered over the years is all available to available data to the actual high-performance compute systems that they use to predict what is going to happen, and also make sure that your drivers have a feel for what they're going to be doing in certain conditions before they actually arrive at the track. And that's it. Thank you so much.